Lesson 5.5 is called double angle, and in this lesson, we're going to look at the double angle identities and product to sum and sum to product identities. So these are very important formulas that we are going to use a lot in our trigonometry class. So double angle means instead of finding cosine of angle A, if we need cosine of 2A, what are we going to do? So cosine of 2A can be calculated as cosine squared A minus sine squared A. This will be the main formula for cosine of angle 2A. And sine of 2A, this is also very useful double angle formula, can be always calculated as 2 times sine of A times cosine of angle A. And tangent of 2A will be calculated using the formula 2 times tangent A all over 1 minus tangent squared of A. As you can see on this chart, for cosine of 2A, we have actually 3 formulas, while we have only 1 formula for the other 2 ones. It's because using the Pythagorean identities, you can replace the cosine squared A as 1 minus sine squared A and combine the like terms, and for cosine of 2A can be also calculated just using 1 minus 2 sine squared A. Or if you have only access to cosine of angle A, you can calculate the cosine of 2A by calculating 2 cosine squared A minus 1. This slide shows us the double angle identities. Our first example is, if we have cosine of 3 over 5 given, and sine of theta is a negative number, so cosine is positive, sine is negative. Let's see, where is this only possible? So in quadrant 4, this is our cosine axis, and this is our sine axis. Only in quadrant 4, cosine value is positive, sine value is negative. So we know that theta is in quadrant 4, so we have to think about the signs for sine and cosine accordingly. And now we're going to calculate the sine of 2A, cosine of 2A, and tangent of 2A. So let's get started with sine of 2A. So sine of 2A has only one formula that we can use, and that's 2 times sine of theta times cosine of theta. So to find the value of sine of 2 theta, we have cosine theta given, but sine of theta is missing. So we have to draw our right triangle, and we have to place our angle theta in one of the acute angles. And we have to use this given information, cosine is 3 over 5. That makes the adjacent side to be 3, the hypotenuse to be 5. So that makes my opposite side to be a 4. So sine of theta, I can calculate it using the right triangle. It's opposite over hypotenuse. So opposite side is 4, hypotenuse is 5. But we're dealing with a quadrant 4 angle, so the sine value must be negative. So for sine of 2 theta now, I need to multiply 2 by sine of theta, which we just found out as negative 4 over 5. Cosine of theta is given in the problem as 3 over 5. And then when we multiply these 3 fractions, we have to multiply all top numbers by themselves and all bottom numbers by themselves. 2 times 4 is 8. 8 times 3 is 24. But it will be a negative number because one of these numbers are negative. And at the bottom, when we multiply 1 by 5, then 5 by 5, we will get 25. This will be the answer for sine of angle 2 theta. Now, for cosine of 2 theta, we have a lot of formulas that we can use, but I'm going to just use our main formula, which is cosine squared theta minus sine squared theta. This is the main formula for double angle formula for cosine of 2 theta. Cosine theta is given as 3 over 5, but the formula requires me to square it. Sine of theta, I had to find it, and it is equal to negative 4 over 5, but we need to square it. According to the PEMDAS, we have to square them first, so this becomes 9 over 25, and then this one becomes 16 over 25. And then when we subtract these two things, 9 minus 16 is negative 7 over 25 is the answer for cosine of 2 theta. Now for tangent of 2 theta, since I have the tangent, I have the sine 2 theta as negative 24 over 25, and cosine of 2 theta as 7 over 25. I can just take the ratio of these two values because tangent is always equal to sine over cosine. So copy the first one, multiply it by the reciprocal of the other one. So the 25 and 25 cancels out. Negative over negative gives me a positive. 24 over 7 is the expected answer for tangent of 2 theta. If you use the formula for tangent of 2 theta as 2 times tangent of theta all over 1 minus tangent squared theta, you will still find the same answer for this question. So again, here, they also modeled this problem as tangent of theta, and then they gave us this problem here. So for example 2, it's a different question. We're going to find the values of the 6 trigonometric functions of theta if cosine of 2 theta is equal to 4 over 5 and theta is between 90 degrees and 180 degrees. So you're looking at the fact that theta is between 90 and 180 degrees. Theta is in quadrant 2, and in quadrant 2, sine of theta is a positive number, but cosine of theta is a negative number. And tangent of theta must be a negative number. Cotangent of theta must be a negative number. Now, and we have the information for cosine of 2 theta. How am I going to use this information and find the 6 trigonometric functions for only theta? So let's remember the formula cosine of 2 theta. We have this main formula, which is called cosine squared theta minus sine squared theta. But we also have the formula as 2 times cosine squared theta minus 1. So this is the cosine of 2 theta is equivalent to this. So that means if I plug in the values for cosine of 2 theta, it's 4 over 5, 2 times cosine squared theta minus 1. We can solve this equation to find the cosine of theta. So I'm going to add 1 to both sides. Adding 1 to 4 over 5 is going to give me 9 over 5. And this is equal to 2 times cosine squared theta. So isolate the cosine squared theta. We have to divide each side by 2. And then when you divide 9 over 5 by 2, dividing by 2 is the same thing as multiplying by 1/2. So I will get 9 over 10 is equal to cosine squared theta. So then I need to take the square root of each side. So cosine of theta will be the square root of this number. So square root of 9 is just 3, and square root of 10 is just square root of 10. But I have to decide whether this is going to be a positive value or negative value. Again, because theta is in quadrant 2 and the cosine value is negative in quadrant 2, this will be the cosine value for theta. If we draw a right triangle and then place our theta, its adjacent side is 3 and its hypotenuse is radical 10. Using the Pythagorean theorem, c squared is equal to a squared plus b squared. We know that this must be a 1 because 1 squared is 1, 3 squared is 9, 1 plus 9 is 10. Taking the square root of 10 is just root 10, right? So now I'm ready to list all the trigonometric functions for theta. Sine of theta is opposite over hypotenuse, so it's 1 over radical 10. Sine must be a positive number. We want to rationalize the denominator, so when we multiply top and bottom by root 10, this becomes the sine of theta. Cosine of theta, we figured it out here, but we want to just rationalize the denominator by multiplying the top and bottom by root 10. So it's going to be negative root 3 root 10 over 10. Tangent of theta will be opposite over adjacent, which is 1/3. And we said that tangent must be a negative value. Cotangent of theta is adjacent over opposite, so it's going to be 3 over 1, which is basically 3 or the reciprocal of this number, but that one will be also a negative number. Cosecant theta is, cosecant is always reciprocal of sine, so if you take the reciprocal of 1 over root 10, you just basically get root 10, and their signs will always match. And secant of theta will be always reciprocal of cosine, and this is our cosine. Its reciprocal is negative root 10 over 3, and this is how we find the 6 trigonometric functions for theta using the formulas. We can also verify that cotangent of x times sine of 2x is equal to 1 plus cosine of 2x as an identity. So when you see these problems, usually it's a great idea to just focus on one side and simplify it as much as possible to show people that the first side gives us the second side when we simplify it. So we're just going to focus this part and we're going to forget the right side for now. So for cotangent x sine of 2x, we know that cotangent of x can be written as cosine of x over sine of x. And this part is called quotient identity, but we're still multiplying it by sine of 2x. We're going to copy this one as it is now, but sine of 2x can be changed to something else because it's called double angle identity. In trigonometry class, sine of 2x is always equal to 2 times sine of x times cosine of x. Now, when we look at what we got here, the top sine x and the bottom sine x cancel out. And then this gives us 2 times cosine squared x. 2 times cosine squared x. 2 times cosine squared x. So we simplify the first side as 2 times cosine squared x. But now when I look at the right side, somehow I have to change it a little bit more. So it looks like 1 plus cosine of 2x. For this, if you remember that cosine of 2x is equal to 2 times cosine squared x minus 1, and I want to leave the 2 cosine squared x alone here by adding 1 to both sides, I get cosine of 2x plus 1 is the exact same thing as 2 cosine squared x. So when I go back to here, 2 cosine squared x is the exact same thing as cosine of 2x plus 1, which now matches with the right side of the equation. That's how we do these problems. Now, when we look at the double angle identities and how we can use them to simplify some of the expressions, for example, questions like cosine squared 7x minus sine squared 7x. So we know that anytime we have cosine squared an angle minus sine squared an angle, that formula is actually equal to the cosine of the 2 times of the angle. So 2 times of 7x is 14x. So this whole thing is actually equal to cosine of 2 times 7x, which is cosine of 14x. So cosine of 14x will be changed as cosine squared 7x minus sine squared 7x. Question B is a little bit harder because we don't have any formula which shows like sine 15 times cosine 15 is equal to what? But I know that we learned a formula, something like sine of angle 2A, this is the double angle formula for sine, it's always equal to 2 times sine of angle A plus the cosine of angle A. So here, if we think that angle A is 15, so I have the sine 15 and cosine 15. So I have this part, but I'm missing the 2. So what we can do is this part is 1/2 times 2 times sine 15 times cosine of 15. So in real life, I'm not changing anything because 1/2 and 2, when we multiply them, they cancel each other. But when I am adding this extra part here, 1/2 times 2, I am now making this part look like the double angle formula for sine. So this is the exact same thing as sine of 2 times 15. And then this 1/2 comes back with me to the second line. So on the third line, we have 1/2 times sine of 2 times 15 is 30 degrees. So this is 1/2 times sine 30. Sine 30 is equal to a 1/2, which will give me equal to a 1/4. This is how we can simplify sine 15 times cosine 15 as 1/4 without using a calculator and combining everything we learned about trigonometry so far. This lesson continues with some additional identities called product to sum identities. So if we have cosine A times cosine B, we can replace it with 1/2 times cosine A plus B plus cosine A minus B. If we are going to find the equivalent for sine A times sine B, we can replace it as 1/2 times cosine of angle A minus B minus cosine of A plus B. Then you have sine A times cos B and cos times sine A. They will give us some relationship with sines. So this chart, you are very welcome to use them on a piece of paper and use the problems to find the answer. So this is what the question is going to look like. How can you write 4 times cosine of 75 times sine 25 as the sum or difference of two functions? So here, 4 can be expressed as just 4. And cosine 75 times sine 25, so this is cos A times sine B case, which is the last case here. Cos A times sine B is going to use this formula, so you will need to write 1/2 first. And then you will need sine of sum of these two angles, which is sine 100. Then you will need a minus and sine of minus of these two angles, which is 50. And then 4 times 1/2 just gives you a 2. And when you distribute the 2 over the parentheses, the answer becomes 2 times sine 100 and 2 times sine 50 for this question. This lesson continues with sum to product identities. And whenever you have questions looks like sine A plus sine B, you can use the equivalent expression as 2 times sine of A plus B over 2 times cosine of A minus B over 2. And you can take time to understand the other formulas whenever a question comes. For example, this example on the slide, sine 2 theta minus sine 4 theta. So sine 2 theta minus sine 4 theta. So it looks like the second formula here. Angle A is 2 theta. Angle B is 4 theta according to this problem. So we're going to use this formula, which is 2 times cosine of sum and half of these angles. It's cosine value. And then we're going to minus these angles, divide them by 2, and then use the sine value of that answer. So A is 2 theta and B is 4 theta. So we're going to add them and divide them by 2. So 2 theta plus 4 theta divided by 2 is 3 theta. And the formula calls for the cosine value. So we're going to need 2 times cosine of theta. And then the other part of the formula requires the 2 theta minus 4 theta divided by 2 and its sine value. So that's sine of negative theta. And because sine is an odd function, this negative goes to the beginning of the expression, and this negative theta just changes to a theta. And this is how we do these problems. Now, when we look at the homework problems and see what kind of questions we have on 5.5 homework, we have a matching problem. So with number 1, I have 6 questions for you to try. So recognize that this is 2 cosine squared 15 minus 1. So if we remember the formula, cosine of 2a can be calculated using 2 cosine squared a minus 1. So in this first question, we have the 2 cosine squared 15 minus 1. So that makes angle A to be 15. But this will be the exact same thing as cosine of 2 times this angle, which is 30. And cosine of 30 is equal to root 3 over 2. So this first one is going to use this, and this is how you're going to find this answer. This one, if you recognize that this formula belongs to tangent of 2 times 15, that's tangent of 30, and tangent of 30 is sine 30 is 1/2, cosine 30 is root 3 over 2. So for tangent of 30, you will need sine over cosine. So you will need 1/2 divided by this number. So multiply it by the reciprocal, and you will get root 3 over 3 here, and that's how you're going to get. So basically, you're going to recognize these with the double angle formulas and match these expressions for number 1. Number 2 is more straightforward. If you look at this problem carefully, this looks like cosine squared A minus sine squared A, which is an equivalent expression for cosine of 2A. So according to this problem, A is 157.5. So 2A will be the double of this, and that's, I believe, 315 degrees. So this whole thing is going to actually be cosine of 315. So to find the cosine of 315, I need to find the reference angle. So reference angle for 315 is 360 minus this, which is 45. So that's equal to the cosine 45. And cosine 45 is root 2 over 2, and that's how we answer number 2. Just like number 3, this question is very similar. Just recognize if this is matching with any formulas we learned so far. This is sum to product identity. So from this formula that we studied before, this chart, this question here, cos 5 alpha plus cos 8 alpha, it looks like this, A being 5 alpha, B being 8 alpha, and you can place it into this formula, and you can find the answer to this question number 5. For number 6, we have seen a question like this. To find the sine 2 theta, you need the sine value and you need the cosine value. Sine value is given, but you have to draw a right triangle and you have to find the cosine value for the same angle. If sine is negative root 6 over 7, opposite side is root 6, hypotenuse is 7. Using the Pythagorean theorem, 7 squared is 49, root 6 squared is just 6, and when you subtract them, this side squared is 43, that makes it equal to radical 43. So you have the sine of theta, but you are also able to find the cosine of theta as adjacent over hypotenuse, which is root 3 over 7. And the problem tells us that cosine is a negative number, so we have to just use it as negative root 3 over 2. Then we have the formula for sine 2 theta, and we have the values to place in. And we have the formula for cosine of 2 theta, and we have the values to place in for number 6. Similarly, for number 7, this time we have tangent of x given. So I have to now draw a triangle for angle x, and I have to place the values for tangent of angle x. Tangent is opposite over adjacent. So opposite side is 3, adjacent side is 1, because 3 over 1 is just 3. Using the Pythagorean theorem, 3 squared is 9, 1 squared is 1. When we add them up, that's 10. So c squared is 10. That makes our c value be radical 10. So now we know that sine of angle x is opposite over hypotenuse, which is 3 over radical 10. And then cosine of x is adjacent over hypotenuse, so it's 1 over radical 10. And tangent x is already here. But now I have to think about the signs. Tangent is positive, cosine is positive. If both tangent and cosine is positive, we're in quadrant 1. And if we are in quadrant 1, everybody is positive, including the sine. For cosine of 2x, we can use the formula as cosine squared x minus sine squared x. And we have the cosine value, we have the sine value. We need to square each of these fractions and subtract them. For sine 2x, we can use the formula 2 times sine x times cos x. And then, so we need to find 2 times, and here is where sine x is located, and here is what our cosine of x is located. Multiply the top numbers, so 2 times 3 times 1 is 6, and root 10 times root 10 is just 10. When I simplify this fraction, it will give me a 3 over 5 as an answer for the second part of this question. We have done this question similarly, so you can use the identities to simplify your expression for number 8. For number 9, it's more simplification and verification. The purpose for this question is so you recognize that tangent of x can be expressed as sine x over cos x, which is called quotient identity. And then you can just, add them up. If you try on these questions, you will find the reasons for each change. This will finalize our section 5.5.